Okay, so again. So, good afternoon, first of all. Well, the idea today is, instead of making a lecture about more centered on artificial intelligence, I want to give you a brief overview of the current research activities on thermography. So, of course, this course is, of course, made for artificial intelligence. We have talked about it in the last two lectures, and I hope that I delivered you something. The point now is to understand what is the current state of the art of the research activities regarding thermography. Of course, all the things that we are going to see right now can be transferred, maybe, on your domain. So we are working with signals, time series, more generally. And the idea, as I said, is to give you this outlook on these strategies for processing those signals, and maybe you have a similar problem representable in terms of signal processing, and then you can make some have some idea. I don't know. So we are working again. So these are few panels that you have already seen before. So we are working with composites. And why composites? Because these are materials, artificial materials, that are made by more constituents that are arranged to increase the properties of the single constituents, of course. So the first one was plywood, where you get some layer of wood that are tilted each other to get some more strength at the end of the stratification. But then there are carbon composite, fiberglass composite, many other composites that you can, as you can imagine, for many applications spanning from aeronautics, automotive, architecture, civil engineering, and so on. This is another panel that you already seen, because we are focusing our attention on the production process. So not during the production, because of course we are making some quality control on finished goods, or at the end of the stratification that could be made manually or with this machine here that you hear on your left. At the end of the stratification, you can have many possible defects. Of course, the production should be good enough to get a low number of wrong, let's say, structures. And but the possible defects can be on many kinds. Inclusions of materials, different orientation errors between two stratification of the taper that is typically used for making panels, or gaps that are wider than a specific tolerance and something like this. So the problem is that at the end of the production, after the polymerization, at the end of the production, all the defects are inside the sample and are very hard to be detected. That's why, so these are some examples with a T-joint, and book effect, resin pocket, so delaminations, or difference in the expected porosity of the whole bulk material. We are applying thermographic inspections as a non-destructive technique instead of many other techniques that you have already discussed in the past. Let's say, for example, ultrasonics or light penetrant or vision systems, X-rays, and so on. Where with our thermography, we are able to detect defects inside the material by looking at the changes of the surface temperature after some excitation of the material with, for example, lamps or laser or microwaves or any other form of excitation that you can use for warm up your material, for warming up your material. So these are the outlines for today's presentation. So we will start with the materials that in our group we have considered so far. So just to give you a brief idea of the variability of the processes, and then some solutions. More or less, we will go through the things that we already see. Differential analysis, so something that is deterministic, and unsupervised learning or supervised learning with feature-based classification, deep learning, or other two techniques that I'm going to show you today. And then some words about the examination. And so let's start with the material. So before looking at the material itself, it's better to make a recap on the kinds of thermography inspection. So first of all, flash thermography, where we have an excitation made with some xenon lamp, for example. So with an excitation of few milliseconds, the temperature rises in a very short time, in milliseconds, as I said, and then there's a decay. So if you compare the temperature decay versus time of an homogeneous region and of a defected one, you will see here that there's a difference. So the starting point for both signals is more or less the same. This is one of the difference between this technique and the step beating thermography. And then the decay. In the decay, you can see here that there's a difference in the profiles of the temperature. Step beating thermography, again, something that you have already seen. We can also change the duration of the input excitation, starting from, for example, 24 seconds till 225 seconds. So this means that with shorter excitations, we are able to reach just the samples that are close to the surface, but with good resolution. Otherwise, with 25 seconds, for example, we can reach deeper defects, but we have lower resolution for those defects that are close to the surface. And again,
sorry, Professor.
Yeah.
What was the input excitation in this case?
For this specific video here, you say?
Yeah.
Okay, so this was, I cannot remember actually, but it was the same of this temperature profile. So this is normalized to 1,000 samples. And if I can remember well, this was the 180 seconds excitation. Okay. That is the one that we use here for this.
No, I refer to what kind of input did you use? I don't know, a laser,
lamps. These were two argon lamps, each one had a power of 500 watts, and were illuminating the sample for, let's say, 225 seconds.
Okay.
And that's
Thank you.
Place, of course, a certain distance. I cannot remember actually the distance of these lamps, maybe 2 meters or something like that. And that were on for the duration of the excitation, and then switch off to see the profile of the decay of the temperature. Now, the other input data are for looking thermography. So here we have a transient analysis, not a transient analysis as the previous two ones, sorry, but a stationary analysis. So once you get this oscillation here that you see here, you can, since you know, of course, the modulation in amplitude of your input excitation, you're able to understand which are the differences in amplitude and in phase, that means delay, of what you detect from your surface and what you emit from your source. Okay, and then you see here some points that are plotted in time, but instead of using these profiles, currently it's typical to use these two maps, an amplitude map and a phase map, where the phase means the delay of the detected, in that case, sinusoidal wave that is detected from the surface of your structure.
Is that in lock-in methodology, so we are emitting and receiving
this at the same time. Yeah.
So it means that it's continuous process.
Yeah.
It doesn't decay. The heat doesn't decay.
There's a decay where, for example, in this case, this was a sinusoidal wave, but actually you can also use, for example, a square wave,
a pulse train.
For example, and then you can turn on and switch off your lamps periodically for many cycles. And then once you get your final illumination completed, you can derive your amplitude and phase maps. There are many ways to get these two maps. So the problem, of course, everything is linear. So the frequency doesn't change at all because everything is linear. The only things that can be different between what you emit and what you detect are amplitude and phase, and that's it. And you can plot it as a map and process those maps there as the input of your image processing algorithm. Okay, I mean, your consideration, for example, let's say in the amplitude, it's quite easy to detect the first line, the surface defects. Maybe with a phase map, you can also go in depth. Well, as you can see here, there are some differences in your on the second line due to the presence, of course, of these defects. Okay, so there's a delay also in due to the second line of defects that is completely invisible in the amplitude map. Okay, and so again, another panel that you already seen. Now maybe you are more inside the problem. The objective is to detect the in-plane geometry of our defect, but also characterize, for example, the depth of the defect, because this is the discrimination between repairing or not your finished good. Okay. The problem is that the surface response, the phase temperature response, depends on many parameters, many properties that are typical of the material, of our composite material, density, porosity, and so on, but also depends on the structure's geometry or the thermal properties of the materials or the spectral properties, and of course depends on your defect, your possible defect. So this is our focus. This was our focus for the past analysis, was a target specimen made of glass fiber and fused polymer, again with the region of interest of those flat bottom. I don't want to waste your time any longer. There are many other samples that we have processed during time. For example, this was made by an industrial partner that we have worked with. Leonardo. I don't know if you are aware of this an Italian manufacturer of aircrafts. And this was a panel made of carbon fiber reinforced polymer and a laminate, very, very thin in thickness. At the end of the story was about 2 millimeters of thickness, and made of many, many defects. They are completely invisible on the surface. I have this panel in the laboratory. If you are curious to see this panel, you can visit me in the laboratory and I will show you this panel, but it's completely flat, perfectly homogeneous. So it's impossible to see from the surface that there are many inclusions within the material.
Finished product.
This is finished, yes. Finished, completely finished. This was made on purpose for making defects, and let's check us our techniques and state whether or not we're working on this laminate. And there were 4 inclusions of materials, and anytime that they placed the workers, who made our panel, placed the foreign object, let's say, for example, the defect D1 of class 1 was placed at the interface between the 7th and the 8th plies. Okay, so in the middle here between these plies at this depth. So this was actually a surface defect. And we made a scan with a profilometer to get the perfect characterization of the size of the material before finish the processing of the material itself. So before the polymerization, when you make an inclusion of some material, for example here, you are still able to detect it visually, as you can see. But then at the end of the polymerization process that is made with an autoclave at specific pressure, temperature parameters, then everything is completely flat. You are not able to detect any inclusion of materials. Okay, so before making a polymerization, we scan it with a profilometer. You can see here the laser line, the profilometer that we have discussed many, I don't know, 2 or 3 lectures ago. So inclusions made of a white paper and of this fluorinated ethylene propylene FEP material. So they are very, very small in thickness, 0.05 and 0.08 millimeters each. And so this is an actual material that is used for manufacturing of aircraft. So this was a calibrated specimen in the sense that we have scanned it with this profilometer, so we know everything about this and we can create our ground truth. But it is not made for. This was made for an aircraft with materials that is actually in our skies. Okay. Then another specimen, for example, was this T-joint. The T-joint made again of carbon fiber reinforced polymer that was scanned with ultrasonics, C-scans. So here, this is the view that here on the bottom of the whole specimen. So you can make a comparison between this is the picture taken from the bottom of this T-joint, and then with this image that is the result of the C-scan. So somebody, an expert of ultrasonics, told us that there were 2 different kinds of defects, this extended delamination, D1 here, and a local defect. We can also identify a pristine region. Pristine region means a sound region without any alteration, perfectly homogeneous. And we have used this region as a master. So everything should be as this master region, and we will compare the analysis of thermography with the specific region here. And we will see here this point right now. This is another specimen, again made of carbon fiber fused polymer with inclusions of 3 different materials, different depths, and so we are getting even more challenging specimen. So you see here that instead of having 1 or 2 inclusions, 2 materials for the inclusion, we get 3 materials for the inclusion. So these Alar, Campton, and metal discs, and with different diameters at different depths. And for all these 4, so this is the material. These are the materials. For all these materials, we get different inspection strategies. So this is a kind of matrix of the data set that we had, that we have processed. For example, the first, the carbon fiber laminate made by Leonardo was inspected just with single flash thermography, and we have processed this single flash because they needed something that should be fast in their production line, and they asked us for a flash thermography. The glass fiber and fused polymer, we already seen something. We get long pulse thermography, but also lock-in thermography, and we have used, for example, the results of lock-in thermography with unsupervised clustering, where we made that let's say example of a supervised clustering in MATLAB, and we will see again it today with many other features and classifiers. Then the T-joint, for the T-joint we get the sinusoidal wave excitation and multi-frequency. So we add just the amplitude and phase maps of the view from the bottom of the T-joint. And then the last one, the carbon fiber fused polymer, this specimen here, we get a square wave excitation, multi-frequency, and multiple source arrangement. And we were copying the problem, for example, for multiple source arrangement. We will see now in a few minutes. So the solutions. As I told you before, the idea is to give you, let's say, an historical overview of how we have processed all these samples, and maybe you can transfer these ideas to your specific domain. For example, I cannot remember who of you was working with 3D analysis, three-dimensional analysis. Maybe the first point, this differential analysis, the first point here could be a possible idea of processing depth maps and compare depth maps with something that is already acquired as an homogeneous region. Let's say here, so we want to, of course, inspect everything automatically. So starting from, for example, this point-by-point comparison with pristine samples, and that's what I was talking about a few seconds ago, unsupervised learning and supervised learning. The last 2, blind linear mixing and blind deconvolutions, are procedures that involves artificial intelligence, but the focus is more on the pre-processing of the data, on the extraction of features, and then using shallow classifiers like SVM, what we have already seen for processing these kind of features.
So what about subsurface effects? How much depth we can go?
And now we will see. Just be patient. So differential analysis. As I told you before, we have used this T-joint for differential analysis. Why? Because we get a region that was certified, let's say, by an expert as a master region, pristine region, so completely homogeneous without any problem, any defect inside. So of course, in mass production, you can obtain a master object. So that would be, for example, a CAD, or also an inspection of something that is surely homogeneous. And so this is information that you probably have in mass production. The idea here was, as I said, to take this as a reference. So these are amplitude images obtained at the end of lock-in. So we are working with amplitude images. These are from region 3. This one, the first one, that is our Christine region. And then region 1 and region 4, that has some defect. Maybe you can just, looking at these images, make so see that there are some differences here. So the problem is, how can I detect these problems that are almost clear in these images, but automatically, without the intervention of an expert like you are looking at these images. So the problem is that, as you see here, images are not comparable on magnitude levels, because maybe you are making some analysis with different room temperature, so your values of the temperature are different. Also, the way you are illuminating your bottom of the T-joint is different, is not perfectly homogeneous. So there's a problem in the amplitude, but also in the space. So we want to make a point-by-point comparison. So I want to compare this point, I don't know, this one here, with some point of region 3 that is our master, that is placed, of course, in the middle of this channel. But if I take the position of this point and then the position here, maybe there's not correspondence between the two images. So we want to register the images and make perfectly comparable with a point-by-point analysis. So processing pipeline, we have a reference data, the master sample, and then a source data, A1. These are amplitude maps again. But the same could be done also with the phase maps. In this case, we were working just for the analysis of amplitude maps. First, input normalization. So again, try to have everything bounded in the same at the same level. Then an alignment of the image, so to make these two ends comparable, perfectly comparable. And then the comparison with some strategy. Maybe you will say, okay, once they get that these images are one over the other, maybe I can just make a subtraction, okay, and say if it is 0, these are perfectly equal, or this is not 0. So this would be the first way of working. But maybe there's something different, for example, cross-correlation, that is able to get more robust results. Okay. Then image normalization. The idea is that we don't want just to have everything bounded between, let's say, 0 and 1, but also to make some processing of the data and highlight those regions of our images that probably are more important. For example, let's look at these images. Maybe at the edges of, if, let's say, if everything is homogeneous, you will see something that is smooth. If you have a problem, maybe there's a discontinuity also in your amplitude map. So we want to focus on these discontinuities. How we can do that? For example, first hypothesis, at the pixel scale, the heat transfer is somehow homogeneous. Okay, this is, so that's just the noise of our measurement setup, our camera, for example. So we can use a Gaussian filter that is used for processing these images. So you can see here, for example, the input and the filter image. And if I take this line that you see here, so this was the profile of the input in blue. And at the end of your filter, so you are cutting all the high frequency, you will see that something smoother. So high frequency probably are more due to the noise at the scale. So of course, this Gaussian filter should be tuned so in order to prevent, of course, the deletion of all the discontinuities that are not due to the measurement noise, but that are due to something that is actually underneath your surface, for example, the defect. So once you are filtering your image, you want to delay the noise, but you want to have also this data here, for example. And then an element by element division. So just divide your amplitude map for pixel by pixel with the filtered image that you get. Of course, everything is bounded in this case between 0 and 1 because you are making a kind of normalization of your image. And then you're highlighting just those frequencies that probably belong to a defective region. You see here that you are making a good result, that everything is homogeneous for the first image, amplitude image that was of the master. And then the other two images, you see that there's something here on the edge that maybe is a possible defect, or here you can identify something that again is probably a defect. So we know that there are some defects here because we know everything about the sample. Now, step 2, we need to make this image alignment. So to get the point-by-point comparison, we have all the images are in their own reference system, and we want to make a comparison. So we need to move the template on the reference. How we can do that? There are many ways to do that, but probably with something that is an iterative algorithm that is try to apply some rotations and translations to the template to move it and get the best matching between the master and the reference. So possible transformation, of course, are translation and rotations, but also scaling, because probably now you are taking your image at a distance of 1 meter, and then 1 week, in 1 week, you will take an image at 2 meters. So also we want to also apply global scaling. So these are the possible transformations that we want to apply. Instead of using directly these images, it's better to get a binarization of the image, because these are much more easier to be handled by your procedures. So this means that we started with the amplitude map filtered, as we have seen before, and then we try to make a binarization of these images. So with a simple threshold, I'm taking those pixels that are over a threshold or under a threshold, and I'm saying that below are 0 and higher are 1. So then, once that we have these lines here, of course, you see that there are many outliers. So isolated points, I hope that you can see on the screen. There are some isolated points here, or maybe there's, like, let's say, salt and pepper noise of this image in that position. So with some morphological filter, you can delete everything that is isolated. So those points that are probably outliers, and then group pixels that are of interest. So go back. We know perfectly know the geometry of our sample. So we know that there's a T-joint, and maybe we want something that has a kind of two parallel segments that are in the image. So we want to highlight these points, in order to get, at the end of my iteration, the superposition of these two lines. Okay. So this line should be over this one better. This one is our template, and this is the reference. So this line should be placed here, and this line should be placed here. So all the possible rotation and translation, and of course, change of the scaling to get this matching of the two images. Now, these are the results, for example. So I just try to highlight the position of the edges. Sorry. And region 3 versus region 1. If you remember, region 1 was smaller than region 3. So, and that's why there's not a perfect superposition of the two images. But at the end of the registration, region 1, that is our template, is rotated to get the perfect matching of the two edges of our T-joint, okay? And then again, region 3 against region 4, we get again that region 4 is slightly tilted and maybe shifted to get the matching of the two images. Now we get something that is perfectly normalized in amplitude, but also in space. And now we can say, okay, try to make a subtraction to highlight the differences. Okay, for example, going back here, if once you get that these lines are perfectly matching these two lines here, maybe you can make a difference of sets. Okay, let's say that this is a yellow set, and this is another yellow set. If you make a subtraction, you will highlight just these points that are possible defects. Instead of using this technique that is, well, valid, but maybe too, I don't want to say too simple, but that's it. We try to use the cross correlation. So our aim, again, is to use cross correlation between these two patches. So we define, so you know what is cross correlation, I mean. Once you get, so you define two different patches on your reference and on your source, your template, so what you are inspecting. So this is what you add, and this is, so the first one is the reference, the master T-joint. The second one is the T-joint that you are inspecting. You take a patch of size m by n. And then on the source, take another patch of size m by m, where m is lesser than n, okay? Now, we can compare these two patches, so patch by patch, these two patching using cross correlation. How cross correlation works, so this is a formulation, but the idea is that once you get something that is bigger than a patch that is bigger than the other, so the template patch is moving on your reference patch, and then there's a dot product between these two images, and then the summation of the dot product.
Like convolution.
Similar to convolution. So the idea is that, let's say in convolution, we are moving this, that is our kernel, on this reference. But here, the point is that you will define another map, of course, depending on where you are moving your template on the reference, and you will see that maybe there's a peak of your cross correlation matrix. This peak corresponds to is placed at the shift positions where the two patches should be almost equal. If your registration was perfect, this was centered in 0. But actually, it is not, as you can see, for example, here. I do these two patches. These are not in perfect point-by-point superposition. This means that your maximum of cross-correlation will be on moving this patch or over this line, so along the vertical axis by, I don't know, 2 or 3 pixels. And that's why this maximum is not perfectly placed on 0, but is placed in another point. So the aim of cross-correlation is to make a fine-tuning of your image registration. Okay, that's why you need to do that, because image registration is made with comparing two images globally. So you are optimizing, you are finding the best rotation and translation and change of scale that globally make your perfect alignment of the template over the reference. But globally, maybe there's, for example, a deformation of your image due to the optics that you are using. Maybe there are many other things that could arise in your acquisition process, and then you need to fine-tune your registration in space. So these are, for example, the best overlapping regions that you get from the past two patches. Once you get this maximum of cross-correlation, this could be a figure of merit of how your patches are equal in your step-up process. You, of course, will take for all the patches of the reference and not the patches of the template. Now, of course, you should normalize your maximum of cross-correlation. So previously this was 16, but this was the result 16 just because these two patches were made of, I don't know how many points to 1. Okay, so you should, if everything was MIM pixels of ones, you will get m squared cross-correlation if both are yellow. Okay, if both of your patches are yellow. So the idea is to make a normalization, so define the energy of the patch. For example, okay, in this case there were 20 pixels yellow, that means at once, and in this case was there were 19 pixels yellow. So this is the required shift to get the best superposition, and then we can normalize easily by dividing the maximum by the summation of the energies and then multiply it by 2 just to make everything between 0 and 1. So this means that if this normalized maximum cross-correlation is close to 1, the patches are, let's say, similar. And this is a measure of similarity between the two patches. If there's a small value of the maximum of cross-correlation, normalized cross-correlation, so this is the case where probably the two patches are not so similar. Okay, and maybe, so this is a warning for you and say there's something in that specific position, that position of the patch of your template amplitude image. Or this could be equal to 0. This is a very interesting point. In that case, your cross-correlation is equal to 0 because, for example, you are comparing patches that are just altered by noise. Okay, and of course, noise, there's no correlation between the noise that you get in the first image and the ones in the second image. And so making a comparison and then taking this value between, for example, region 3 and region 4. So creating those patches and moving the patches and so on, we get a minimum of the maximum I know that is difficult. A minimum of the maximum of normalized cross correlation in the specific point. That means that there's something here. Okay, there's a difference between the two images in this similarity measurement metric. Okay, and then we can for sure make a threshold and just say that we get this threshold of 0.25 and remove all the connected components that are too small, because maybe these are not defects but due to other processes, your noise or something like that, and get the detection of this spot here that is also validated by the C-scans, because this was the punctual defect that was found by the expert of ultrasonics. Then, for example, the comparison of region 3 and region 1, we get these other regions here that with the same thresholds and so on. So what's the point in this analysis? That actually we don't have any characterization of the defect. So we are just selecting some pixels that have a defect, but we don't know where's this defect, where's in depth or any shape in the third dimension. We just have an in-plane characterization. This could be enough for testing the quality of your finite good, but maybe it's not enough for our scope for sustainability of the process, for reducing costs, for reducing the number of objects that are rolled into your bin. Okay. And so unsupervised learning. We are now going back to the example that I showed you in our past lecture for the analysis of amplitude and phase maps from lock-in thermography. So we are working still on, again, on lock-in thermography, amplitude and phase maps, and with the sine wave excitation, in that case, this was the frequency of this specific sine wave excitation. We're just taking one frequency, so we are not approaching the problem of multi-frequency. So we just have a single sine wave, and we are trying to detect the defects in a sense, in an unsupervised sense. So we are supposing that we don't have the labels of the ground truth, so we are taking the whole amplitude and phase map as they are, so like this, and nothing more than this. So again, with what we have already seen in the example, in the MATLAB example, maybe you can take this code and try by yourself to make more analysis like the one that I want to show you now. So start with the input enhancement, and we have seen how to make the equalization of an image, the reason why we do that, and use, for example, phase images. So we will, actually, I don't think that you can see that this was blue and this is gray. So we will compare equalized phase results from equalized phase images with the results using just phase images as produced by the camera, not the camera, but by our setup, experimental setup. Then there's a feature extraction problem, and we will compare the results from speed up robust features, the surf features that are very, very similar to the SIFT ones that we have discussed in our lectures, and the histogram of oriented gradients that we have already seen. Just make a comparison of these two, of using these two features, and then classification with something that we should know, hierarchical clustering, k-means, k-methods. Maybe k-methods we haven't discussed about chimedoids. So it's very similar to k-means, but the difference is that the position of your centroid of the cluster is not equal to the center of mass. So the minimum of the average of the position of all the samples in the clusters, but by the median of the position of your in the feature space, of course, of your examples that are that belongs to your clusters. And then, so the comparison of the face map as produced by the sensor, and then the one with the histogram equalization. So this was the histogram. So you see here that this scale goes from 0 to 255. So this is the dynamic range of the unsigned integer, unsigned char, the integer of 8 bits. So this means that your values are more or less all concentrated in this region here. So using histogram equalization, we want to spread these bins on the whole dynamic range of our image. So we are spreading these bins between 0 and 255. So enhancing means, in this case, making, for example, improved contrast in your image. So that would be probably, I want to increase my sensitivity, okay, by changing the contrast of the image. You can define also your specified histogram, so you can define your own histogram distribution that maybe works better for your problem, okay? Now, so once that our phase shifts are equalized, maybe we can transform in all the points of our domain, of our special domain, we can transform these phase inputs that go from 0 to pi in terms of features. And then, as we have seen, we've seen in our example that we made the use of surf features. And we created, for the amplitude and phase maps equalized, two different vectors of features, 64 features, if I can remember well. For comparative purposes, I can show you also the results with the log features. Okay, so we are taking into account these two features, but there are many other features, or you can also define your own feature for your problem. And then for the classification hierarchical clustering, where in an agglomerative approach, we are merging those samples that are, let's say, close each other, close in the sense of some distance metrics. That could be the Euclidean distance or many other distances, Anolabis or Chebyshev or any other distance you can define. Here we will use just the Euclidean distance, as in our example with MATLAB. And then for, as I told you, for comparative purposes, comparison with the k-means and chimedoids. Okay, of course, chimedoids should be better than the k-means, because if you have an outlier in your cluster, this outlier shouldn't cooperate, let's say, to the formulation of the centroid, because when you take the median values of your set of points in the feature space, they should be removed as a result of the median computation. In the mean, in the average, they should cooperate more to your computation of the centroid and place the centroid, for example, in a wrong position, okay? Now, so these are the results of the clustering made with just two classes. So you see here, gray and blue, made with three different clustering approach, and the surf features and the log features. As I told you some days ago, maybe it's better to increase the number of classes instead of taking just 2. Even if you want to have a discrimination between sound regions and defective regions, maybe it's better to define more clusters, just because if you want to create just one cluster for all the possible defects that you can have in your sample, maybe you are creating something that has a very high variability inside, and maybe just one class is not able with your features to describe the contribution of all your samples of the defective class. But let's say just comparison. Key means versus key methods with solved features. Key methods works better in the sense of reducing the number of false positives. Key methods against versus H clustering on the same features, we are even reducing the false positives. And that's why I show you the example of hierarchical cluster with hierarchical cluster. Then, in terms of sensitivity, just comparing with the same clustering approach, the hierarchical clustering, comparing, for example, the OG features and solved features, we see that using the solved features improve your sensitivity by 80%. Okay, that's for comparison, and that's why I just show you solved features with hierarchical clustering. But this was the result of another, let's say, of a design of experiment. Okay. Now, using the equalized phase image, we get more or less the same results, reducing the number of false positives, and then increasing the number of classes. So till the case of 4 classes, where, for example, we can group points, these purple points and green points as a local homogeneity. Or these points here in red that are related to subsurface defects or let's say extended defects with high confidence. So we don't know nothing at all about the labels. So we are discovering the knowledge. So we are trying to understand the results. So that's the point of unsupervised clustering. Okay, and then, for example, these blue points would be local defects with low confidence. Okay, so we know that these are the edges, and there's something here, for example, that is a point of a second line of defects. But as we don't have any information about the labels, we are just making an assumption about the confidence that we get for detecting defects. So once you have this, let's say, complex map, maybe there's a need of cleaning, so to get a deeper understanding of the results. The idea is to use some morphological analysis. So in image processing, morphological analysis means that you work with something that is binarized, first of all, and then you're trying to work on the silhouette, on the shapes of your connected components. For example, using erosion, dilation, or closing the voids, or opening your voids, depending on which kind of filtering you want to set up for processing your data. For example, here we use the all filling. That means that at the end of the morphological approach, for example, also reducing, cutting those connected components that are too small in the area, or removing connected components that are too high, because you probably know. So when you work with companies, nobody will say, okay, that's my substrate, my laminate, find everything. So you know which are the possible defects that you can have in your own material. So you have some idea of the defects that you can have. So, and you need to translate this knowledge of the possible defects in terms of morphological filters and try to manipulate your data to get something that is easier to be processed. For example, here there are in this orange region, probably these are false positive due to a boundary effect. So, because your laminate was, of course, has some boundary, not was infinite laminate, and then there are problems and you interpret your your phase maps, and you get some delay, but not due to the defects, but to the boundary of your panel. But also there are these regions of extended alterations that maybe are related to something. And this was actually the truth, because in that specific investigation, there were some resin clusters on, so this was not polished before doing the analysis. Okay, so these were actual defects, let's say defects, but were agglomeration of resin on the top of the specimen, even if these are not part of the ground truth, of course. Okay, and now with this unsupervised clustering, we have discovered, for example, that there are some defective regions, a line of defective regions. So, for example, we can, in this case, answer to your question, which is the depth that we can investigate. With this, it depends, as usual, it depends on the technique that you use. With this lock-in thermography, with this specific frequency, we were able to find just this line that is 7 millimeters in depth. So we are completely blind to those defects that are below, under this threshold. But it depends. We are blind because we are using this specific technique. Now, later, we will see that we can go to the third line of defects using another approach, experimental approach. So this depends on, of course, the processing that you have at the end of your experiments, but also, of course, on your experiments. So, and you can assess this kind of analysis once you are making unsupervised clustering, once you make this process of knowledge discovery, okay? Because you don't know nothing about this sample, and I just make, for example, the analysis that there was a line of alterations, nothing more than this. But then I move, of course, to the calibrated specimen and say that this line was at 7 millimeters. I cannot remember. So, but there's a point underneath with this specific experimental setup, in thermography, and with this frequency, I cannot go farther in the depth. Okay. Now,
exploratory lenses.
With
Exploratory lenses.
Sorry.
Exploratory lenses. Like exploratory.
Yeah, that's the point of this knowledge discovery. Okay, so I don't know nothing at all about this, and now I'm discovering that with this analysis I can get these results.
How can you label it?
Because actually I know the calibrated specimen, so I know that there's something. So I'm just saying, okay, let's say that so as I'm using unsupervised clustering, I'm representing everything in terms of features, okay? And I will say that these features are the best. So I'm taking the hypothesis that the processing pipeline is fixed, is perfect, and is working. So I'm moving the problem on the experiment. And I want to say, with this specific experiment, can I detect on this material, on this specimen that is calibrated? Can I see something that is, for example, on the second line of rows of defect? Sorry. So the answer is not, because in my discovery knowledge process, I don't see nothing on the second line. So I have to change, for example, the frequency. Maybe with a frequency that is lower, I can go in depth and try to touch also the second line of the defect. So this is the explanation of that we can get from unsupervised learning. Okay. Now, let's move to supervised learning. So we want now to make a model to characterize the defect where we know everything about the defects, so we know that where these defects are placed or something like that. Now, the feature-based classification, also this classification strategy has been already discussed in the past lecture with the example. So you can use the code for your activities if it's possible, if there's any symmetry, let's say, with your problems. So here we want to process the thermal maps. We are working with long pulse inspection of the same specimen, the glass fiber FU specimen, but with long pulse inspection. And make some analytical model approximation, and then classify with shallow classifier, SVM, so this kind of classifiers. Decision trees and ensembles. So we have already seen something in our, let's say, experience, laboratory experience. And this panel, I think that is the 5th time that you see this panel. So the temperature decay, once you get some defect at the specific depth D, in theory, as resonance behavior, and then you can model it by this summation of terms, of exponential terms, depending on the order of your exponential or this term R that is related to the contrast in a thermal way between the discontinuity that you created. Okay. Now, that's what expected in reference perfectly linear, and then moving your defects close to the surface, you will touch in shorter time. So your difference between the reference should be highlighted at shorter times. Okay. And once you get your defect more in depth, your difference, for example, could be at, I don't know how many seconds in this case. So as I told you many times, instead of using the direct temperature, typically we use temperature contrast. Temperature contrast is the difference between the temperature that you get from your actual, from your surface, okay, minus the expected temperature for all the time samples that you get from an homogeneous region. This is the temperature contrast. And again, you will say, how you can define this green term. For example, taking the whole surface that I have and making the median value. Because you know that probably your defect is very, very small in comparison with all the background. And then I will pick just the median value, and maybe this is a representation of my pristine region, let's say. So you can make this inspection even from your current specimen, from what you are testing. Because in any case, your defect should be small if your process is good enough to produce something that has very few flows in the middle. Okay. So this is the difference between these two terms. Of course, we are taking this one out of the play, and then this is the only term that is contributing to the thermal contrast. And these are the profiles. So if you have, of course, no defects in your area, this difference is equal to 0. So your temperature contrast is perfectly 0. In other case, if you have a surface defect, you will get something that is now reaching, this difference is very high. Or if your defect is more in depth, you will get this kind of profile. And if your defect is very, very deep in your structure, you will see something that is close to 0, because you are no longer touching your defects with your heat wave that is going inside your material. Now, there are many ways to process this data, and this is the result. So just taking these terms and making some developments, you obtain this formulation that can be modeled, as you have already seen in the MATLAB code, by this model that I easily created, where this A1, A2, and A3 are features. So from all the signals taken from a single pixel in the image that are temperature profiles, we can make an approximation and try to find the best parameters that are able to fit this model on this guy here. Well, not actually this guy, but on your actual surface temperature, okay? In theory, this was the normalized contrast on the left from the theory, and this is the model approximation using specific parameters of A1, A2, and A3. These three terms are our features, three features, to represent the whole profiles of the temperature contrast in this case. Now, these are temperature decays, temperature contrast from actual points taken from our specimen. You see here that there's a kind of similarity with the results here in theory. And then I'm using a filter, a finite pass filter, that is a digital filter for processing signals, just to reduce the noise, and then make our model approximation. So these curves here are the curves that we obtained by A1, A2, and A3 obtained by a linear a fit of the model on the actual, well, not the actual, but on the filtered temperature contrast. Okay. Now we can represent the whole video of the temperature decay with these three maps. Similarly to what we do with lock-in thermography, where the whole video is represented by the amplitude and phase map. That has a physical meaning, of course. Amplitude, the difference of the amplitudes, and then the phase is the relative decay with what you send to your structure. Here, these features has a mathematical meaning, but are, of course, a representation of the process. Now, three maps feeding a classifier. Before feeding classifier, I took these features in our example and directly make a vector of 3 entries as input of the classifier. That is the first point. But instead of using these three features, for example, I can take a patch. So this is the way. So taking a point from a single pixel from the three maps and then creating a feature vector. Sorry. Instead of using this representation, I can take a patch around my central point, and then let's say in this case a patch of 5 by 5 elements. So these are the features, the three features, and then arrange everything in a final feature vectors that in this case is 25 by 3 elements. Okay, why? Because in this case, I'm taking into account also the contributions from the neighbors of the point. I'm not making a decision of what is this a defect or not, and classify this kind of defect based on the pixel, but taking also into account the neighbors. In that case, in a patch of 5 by 5, I used 3 by 3, 5 by 5, 7 by 7. Of course, once you increase the feature vectors, maybe you are taking into account more information, but at the time, you are making more complex the work for your classifier. And maybe you are taking more time for make just one prediction or for training it. So you should always take the best trade-off between time, computational cost in general, and the accuracy of your results that you get at the end of the story. Now, for example,
is manual or theoretical, or how can we select the features?
in this case, I created this model. Okay, that was able to represent the theory. Okay, and these are the three features. But then I will show you an example, and we will see it in 30 minutes, where also the model is defined by the machine, just driven by the data. And you will see at the end that this model is very close to the one that I defined, but better, because it's derived from the data, is close is close from to what I defined here. Okay. Now, classification, I used a decision forest. I made lots of experiments. In our case, for example, I showed you neural networks, SVM, ensembles, decision tree, KNN, many things. The best was decision forest. That is an ensemble of decision tree. So if you take a decision tree, you are just make a prediction based on a single tree. In that case, I took 30 decision tree, and then with the voting mechanism, decided for the best prediction for the specific class. Let's say that 20 trees said me that this was this signal. Well, actually, this patch of features belonged to class 1, and the other 10 said that belong to class 2, I will decide for class 1, just a voting with the majority of the votes from the 30 trees. Okay. Now, training, good accuracy in training means that my features are able to represent the whole, not only the feature, but also the classifier is able to work with this feature to represent the whole behavior of the temperature. Okay, that's the point. So when you look at training accuracy, if this accuracy is high, this is very, very high, means that your features are discriminative, and your classifier is smart enough to work with this feature to classify the output. Okay. Now,
Is that ensemble and decision tree as the best approach in this?
In this case, I didn't show you all the results, of course.
Decision tree is similar to graph theory.
In decision tree, you say, yeah,
similar to graph theory.
Perfectly similar.
So, what is the difference between the CN tree and the graph theory if we applied the graph theory methods?
Because here you are using attributes as the nodes of your tree, and then the leaves at the end of your tree are the classification, is full of the classification for the specific input. Okay. And you start from one node to several leaves. Okay, so from the roots, there is one. And then you split your signal until you get the final leaf, and then you make the classification for a specific tree. And then you make it for many trees until you get the final classification with the voting. Okay, that's how it works in decision tree. Okay, now classification test. Of course, the results are worse than training, and that's a good point, because it means that I'm not making, let's say, something that is not so perfect, that will give you an idea of maybe I'm not making a realistic analysis of my data. If I get this 99%, maybe you are.
I think there is that difference. How much training achieved and how much testing achieved. There's a difference between testing and training accuracy.
But you make this difference on the top of your processing. You split your data set at the top to train your model with few examples. And those examples are not feeding, so test examples are not feeding your model for training. So these are completely new for your analysis. But these two sets should be somehow different, because if you are training, taking points that are close to the one of your test, maybe the behavior is completely the same, and you will get 99% of accuracy in training at the same 99% in testing. So this means that you are joking with your data. So this is not actually possible. But say, it depends. It depends. So there's not a recipe that say that you should have 95% in training and 92 in test. I don't know. There's not an answer for this question. So it depends. But maybe if you get 99% training, 99% in testing, this should show your light should be on and say, maybe I'm making something wrong, or I'm so lucky that I get the best. So maybe you can publish it. I hope you for publishing it. But any referee should say maybe take care of your data. Maybe you are.
Usually, the literature when we study literature, they usually it's like they show that we have 95% accuracy, more than 90% accuracy in testing and also for training.
35.
95, more than 95.
But depends on your result. For example, many of the deep neural networks that I show you in the past lecture get very impressive results, very impressive accuracy. But it depends, because this is the results of years and years of research, and networks that are even more complex as the time goes on. So it's reasonable that you get 96, 95, 96, 99.
But the gap, they didn't mention the real gap. Literature didn't mention the gap, that the testing and training has this type of gap, like 10%, 5%.
Okay, but because these data sets are typically fixed. In computer science, you may, there are challenges, okay? When there are many conferences where some workshops are organized to make challenges. So they take some data set, but these data sets are already divided in test and training. And they made this test, knowing the images, for example, that are inside, completely different from the training. So it's somebody that has already understood your data set, and then at the end saying, okay, training and test are completely different. And even if you don't have your gap between training and test, this is not due to the fact that the data are comparable, but it's due to the fact that your network is able to generalize, and you are getting okay, good results. So it depends on the data. In this case, where data are very has very low cardinality, you don't have many specimens, because when you work with companies, it is reasonable to test everything to 1, 2, 3 calibrated specimens. And then once you say, okay, I'm able to detect these defects here, I can move to the production line. This is acceptable, and is actually done in the companies. In this case, you get 3, 2 calibrated specimens, so your data set is very short. And maybe to get better results, it's better to move to simulations, for example, using console, let's say, and then try to make to be sure that your model is able to generalize, working on data set, on synthetic data set that are made with console, let's say. And then again, move your model to the reality, to the actual data from your production line. But now, In classification test, we get these results. So actually comparable. This is balance accurate classification accuracy. These are the times, and of course, time increases as you are increasing your number of entries of the feature vectors. Okay. Now, sorry. Well, actually, this is a very it is not too impressive. Okay, this was impressive 8 years ago.
Okay.
Okay, but now this is not impressive. So we are not working on this machine anymore.
Oh, okay.
Because this is so now there are many other machines,
Okay.
more workstation, high performance computing resources that are available. Okay, and then the results are in terms of the per sites. You see here, for example, that increasing the number of per sites make your detection better. For example, removing false positives or closing the hole, and you are getting these results even detecting the second line of rows now because you are using a long pulse thermal inspections. And then with this long pulse thermal inspection, you are able to touch even these defects that are inside deeper in your material. Okay. And maybe 5x5 is the best trade-off between the time required and the results, the accuracy of the results. Okay. Now, the same procedures also used for flash, so no step heating, thermography, with flash thermography and another material. So this the previous one was a glass fiber, and this one is carbon fiber. So to even try to test the generalizability, sorry, of the method with respect to the excitation, flash instead of long pulse, and the material inspected by that we are inspecting. Also, in this case, we get a good balance classification accuracy, 86.9%.
Now you have changed both material and methodology, both.
Both excitation and material. Yeah.
But the results, how can you compare it? You have changed the materials and techniques both.
I'm just using the same technique. I'm not comparing the results. So this 86.9% is not comparable with this 77%. I'm not comparing the number. I'm just saying that I'm able to use the same processing on different inputs.
Okay.
That's the point. Okay. Here we can use flash because, as I told you before, this laminate was very thin. So I don't need longer excitations to go below 7 millimeters. Just with the flash, I can inspect all the material and also classify the results. So this is the ground truth on the left, and these are the results of the processing on the right. Now, deep learning. Okay. I want to take a break, but I want to show you before this point. Maybe before preparing this analysis, I have 5 minutes of break. Okay. So deep learning. The first approach is to use, let's say, image-based deep learning just to discriminate defects or not. Defective region from sound region. So the ground truth is this one. We are working on this carbon fiber and fused polymer laminate, but the specimen, not the one made by Leonardo, the one made with 3 different materials, different depths. So we are taking 2 classes, black background and red something inside, without any other. So the problem here was, can I generalize the approach where changing the sources of excitation. So if you take this image, for example, this is just a frame taken, I don't know where, when. I'm isolating these 3 points, 4 points, or where there's another point, but I cannot see it. And even if the source is the same on the whole laminate, of course, the temperature, so this is an arbitrary unit, of course, it's not 500. In arbitrary unit, the temperature are different, okay? And depending on the configuration of the lamps, so here we get these 6 lamps, halogen lamps, and that were, switch on differently. For example, in configuration 1, these 3, configuration 2, these 3 here, on taking the other off, and so on. Okay, so changing the configuration on the lamps. So the idea is I'm working with a laboratory setup where lamps are in specific position, everything is perfect. There's a repeatability that is of a laboratory analysis. But if I move everything on the production line, maybe my results are not so good, just because my input was not perfect, was not able to illuminate everything homogeneously, but there's a difference in the temperature instantaneously captured from the surface. Okay. Now, we are using an image-based approach. So we are working with the videos instead of the signals. So videos of temperature, okay. Somehow similarly to what we have done here, because if you consider a patch, we are not working on single signals, but on, let's say, 25 signals that are grouped by the square patch, okay. Now, so just a pre-processing of the data. Pre-processing is always needed for the purposes, and then starting from the original image, just one frame, we take a bilateral filter and a Gaussian filter. So these are 2 filters that are at the state of the art, so not the state of the art, that are very well known in the literature for image processing. In any book, you can find this implementation of these filters for image processing. That Gaussian filter is the same that you've seen before. So just taking out.
There are other filters also, but why these 2 are your selected ones?
Because my point was to create this, to have this kind of discrimination. So I used Gaussian filter and the bilateral filter. The bilateral filter was actually similar to the Gaussian filter, with a difference that is preventing the edges. So the sigma of your filter depends on the contrast that you see in your image in that specific point. Okay, so whereas there's an edge, your contrast is high and your sigma should be lower than the one that you use when everything is homogeneous. And there is where you want to remove noise, okay, random noise. So once you get the difference of the images, you imagine that you start from this, comparing these 2 signals that are very close to each other from an effective and sound region. When you make this filtering and then the difference, so you are enhancing this difference. Instead of having these profiles, you are having these 2 profiles that are very different, not only in the amplitude, okay, because of course this jump here is the same that you get here, but also in the shape. A sound region is quite flat, while the defective one has a profile that has some shape, okay. I want to enhance the difference between the 2 signals, okay, by applying the procedure to every single pixel of the analysis of our domain. Now, the network architecture. So in this case, we proposed this network architecture. So this is the result of many test. Okay, so if you say, how can I define my own architecture? Maybe you have some ideas, but then, for example, the number of layers or how you create these layers here is up to you. It's a kind of trial and error phase where you start, of course, from the knowledge of the network. For example, here there are two different blocks. So the first one is an input layer, just to taking videos, because we are working with videos. Then there are 5 TRB, this temporal residual block. Okay. The temporal base block are made like this. One-dimensional convolution, because we are working with signals. Batch normalization, rectify linear unit. The first one, okay, is tried equal to 1, because I want to go to see what is happening with a very high granularity. Okay, so taking sample by sample, because my stride here is applying on the time. Okay, because I'm making a one-dimensional convolution over time. Okay, so if stride is equal to 1, well, this means that you are taking your kernel and you are moving your kernel by steps of 1. So you are making a kind of fine analysis of your input signal. The second one, for example, we use a higher stride, because we want to make a kind of generalization of the analysis. Okay, so taking a new representation, starting from this, and then jumping more, and then jumping more, so improving our stride. That was the initial idea. But then the number of the stride, trial and error. So that's the point. So the basic idea is something that you can imagine in your in your brain, but then the selection of the exact value is a result of trial and error. So make tests and say the best accuracy I made with stride 3. First one, stride 1, second one, stride 3. Then, for example, here we used residual connection. So the input was then summed to the output of these 2 blocks for making the training faster. Okay, that is, as we know from the literature, that making this kind of connection makes your training faster. So you are reducing the problem of the vanishing gradient that we've seen 2 days ago. Okay, and then 5 times this block that is made of these other blocks, and at the end a one-dimensional convolution that was made just to get an output 2 by 1, where the 2 entries are the probability of that specific input to belong to class 0 or class 1, sound or defective region. That's the architecture. Without pre-processing, so then another point, we are using the same analysis. So we are using the same sample, but with different configuration of the source. So actually the numbers are different, even if the position of the defect is the same, obviously. So taking, for example, these 4 configurations of the sources for training, and then using this one for testing, we make this without pre-processing. So this is the ground truth. And with pre-processing, we make a good segmentation of the defects. Okay, for example.
So this is done by frame by frame video.
Taking the whole videos and then working with this network on single signals, but also, so this stem block actually has a kernel that has a special size. Okay, so it's used on video, but this size is not one by one in space. So if it was one by one, I can process just one signal in the third dimension. It was actually 3 by 3. Okay, so to take into account also the neighbors. So that's and that's why I'm saying that it's a kind of image-based analysis. Okay.
What about the batch normalization?
The batch normalization, in what sense? What does it mean, or
No, what's the requirement here?
for the batch normalization for that one?
Yes.
So for any batch of your that you get in your input, you're making normalization of the data to take your data passing in this layer, normalized, so to avoid that one, for example, one representation has numbers very high and the other representation has numbers that are lower. Okay, so that's the significance for this normalization.
Assume that it may lose the features, or it will enhance the features in this context.
For batch normalization. So the question is why I'm using batch normalization for that problem? Because, well, actually, typically we use batch normalization for that problem. That if you, well, you can also not use batch normalization, but the problem is that if you go back to neural networks, for example, you use an activation function to get something between 0 and 1, let's say. Let's see the.
Usually, we use this normalization before feeding the data.
Yeah, but this was for preprocessing. Okay, but then once you are going deeper in your network and you're creating new representation, these are a convolution is a summation. Okay, maybe you get that your kernel that is obtained by the data has numbers that are not comparable with another kernel of the same filter bank. Then that's the requirement. So for that case, use this batch normalization, because if not, you are just using few kernels instead of the whole kernels of the filter bank, because you are just working with not so many neurons as you have defined, not so many kernels as filters as you have defined, but just for one that as a training, your kernel was of huge numbers, let's say in magnitude. That's why, just to spread the information on all the kernels, okay, that you have in your filter bank, in your layer. Now, these are the results, and then changing the test configuration and making some average. So for the balance accuracy, for example, the average was this one. So the problem is that anytime you work with something that is related to images, your model can be biased by the shape of the defects that you get in your training set. Okay, so maybe you are creating something that has a balance accuracy of 87%. That's very, very good. But once you are testing an actual defect that has not a perfectly circular shape, but I don't know, a bolt. Maybe in this case you will not able to detect this kind of defect. Okay, so even if your results can be better for that specific analysis, maybe in the reality, once you move to the actual production line, your accuracy can decrease a lot. Okay, you say, but it doesn't work for anything. Now, the problem is that you have to increase the training set, taking more and more examples of more and more defects to make your model capable of interpreting any shape of defect that you get in your training set. And then, of course, in the test set, once you are working with the actual inspection in the production line, where you obviously can have everything, any kind of shape, any kind of defect, and so on.
What does this mean, balanced accuracy?
So the balanced accuracy is an accuracy scaled by the population of the class. So for example, let's say that you have everything background and then just 1 point of defect. In that case, if this point is not detected, your accuracy will be 99.999%. Balanced accuracy will be 50% because you are normalizing by the population of your data set. So this means that you are perfectly your accuracy is 100% on class 0 and 0% on class 1. The average, 50%. Of course, this is lower than the actual accuracy that you will get. Not because your model is working fine, but just because your test set was really unbalanced.
And
Okay.
also it's biased.
And
the result is biased then.
In that case, yes, of course. So a model that predicts everything background is the best one if you look at the accuracy. Okay.
CN and recall.
Yeah.
That recall is the important point.
In that case.
For repetition.
Not for repetition, because okay, recall is more related to the sensitivity. Okay, so if you have a defect, you have the probability of the 76% on average to detect this defect. Okay, and of course, if you work with aircrafts, it's better, even if you are creating lots of false positives, false predictions of defects, it's better that anytime you have an actual defect, you are able to recognize it. That's the point of recall. So it's better, it's preferable to have a good sensitivity to the defective class, okay, instead of the best precision. But in that case, in your case, maybe it's not.
The precision and recall are contradiction sometimes.
Because precision is, once you have a prediction of defect, is it true or not? That's prediction. Precision. No, that's precision. Okay. Anytime your prediction is of class defect, is that the truth or not? So this is the precision. The recall is slightly different. Anytime you have a defect, are you able to detect this defect? Sensitivity. Yes or no? So in that case, I prefer, for safety reason, to have an enhanced recall instead of precision. But, well, actually, it's better to have both equal to 1, right? But if I can, when I decide which model is the best, and I have this similar accuracy, balanced accuracy, maybe I will move to the recall metric to say, okay, my recall for class defects is higher with this model than this other one, and I prefer use this model, this architecture, let's say, instead of the other, when the balance accuracy is the same, it's close. Okay. Now, further activity, use multi-frequency, because you know that we are working, we can work, for example, with lock-in thermography, right? When you work with lock-in thermography, you should select your period of excitation, your frequency. If I use a long period, maybe I can go deeper in the material. If I use shorter periods, I can go not so deep in the material. An analogy with step-heating thermography, okay? If I compare these two, the results of the investigation with different periods, I can have another degree of freedom that can help me in making the classification of the defects. For example, if I see a defect with shorter period, with longer periods, and that's it, this defect probably is deeper than a defect that I can see with shorter and longer periods. Okay, so I'm adding more information, but I need to use all the data, and this is an activity that we are now working on. Okay. Then making signal processing. This is the example that I showed you 2 days ago. So, for example, making some normalization of the data using, for example, data that have been acquired with different excitation, and then squeezing this data in, squashing this data in 1,000 time samples by resampling of the data, and then normalize it between 0 and 1 with this typical normalization. Then I will get, starting from these images, from these signals, so I will get something that is like this. Instead, that is bounded between 0 and 1,000 samples, and then between 0 and 1 in the amplitude, just input normalization in terms both horizontally and vertically, right? Then use convolutional layers with one-dimensional convolutional layers, rectified linear unit, max pooling. So the difference between the previous one is that in that case, I'm not only saying black and red. I'm adding the information, the class, depending on the depth of the defect. So my ground truth will be like this. So 3 lines of defects. The first line of surface defect, then middle depth defect, and very in-depth defect. I'm using this ground truth that is different from the one that we have seen, but you know how you can create your ground truth, and if you want at home, you can run again the code taking this ground truth, and say, okay, separation, test and training. All the points of the test are used for the analysis, and I will randomly pick only few points of the training to make a balancing of, to balance my data set. Okay, just because class 0 has many examples if compared, more examples if compared with the other classes, the effective classes. Here I get these 3 classes, and of course these are limited in points. And then split between training and validation. So there are some points here in green that are of the validation set in 75% splitting. Okay. Results of the training, of course, only on the side, because I'm just working on the side of for the training set. So when you have these results, this means that your network, that is very easy, just 4 convolutional layers and nothing more than this, and then fully connected, very easy architecture, are able to detect the defects that are on the 3rd line. Now move to the test and say, am I able to detect the test? Well, actually yes, but only with excitation time of 180 seconds or 225 seconds. Okay, because of course I need time to reach the 3rd line of the defect from the experiments, not from the test. With a good balance accurate classification accuracy, 84% better than the previous one, but the previous one made with the analysis of the features from the analytical expansion in my model, we're not taking into account the 3rd line of defects. So now the network, the deep neural network, is able to find some representation, some feature representation that is capable to represent also the defects of the 3rd line. Okay. And So these are the probabilities, but maybe a step forward. Classification scores can be also improved, for example, looking at probability. So at the end of the network, I have a softmax layer where I'm working with 4 classes. There is a vector of 4 probabilities. Now I'm taking the entry of the first element of this vector and reshaping it to have the probability of class 0. This is the probability of class 1, class 2, and class 3. Of course, class 3 has lower probability to be detected. So if I want to push the classification accuracy of class 3 forward, I need to change the way I pick these points as points of class 3. So at the end of the softmax layer, if I have, for example, 0.3, 0.1, 0.1, no, not so good, 0.3, 0.2, 0.2, 0.3, maybe I will predict for the first one, because, okay, are very close each other, but maybe for the first one, because the third decimal is higher. But if I want to help the recognition of class 3, I can select a threshold, a global threshold, that anytime my probability of class 3 is higher than 25%, I will label this point as class 3, even if there's another entry of my vector that is higher than the one of class 3. Okay, and that's what we have done here. So we are improving the recall of class 3. So that's for the point. And of course, we are creating false positives, but it's not our problem. Then, in any case, we are making warnings. So for experts that then should go there and say, okay, there's a problem or not, and then I will check my sample. Blind linear mixing. So this is a very interesting way to improve the results. So your question before was how did you select the model? So why did you use this exponential model with these 3 features and so on? I said, okay, just looking at the profiles expected in the literature, in the theory, and then maybe this one is a good approximation. And I take my paper and try to write down some models, mathematical models, and then check it, plotting it on MATLAB, for example, and say, okay, these 3 features are enough. But was my ability or inability, because maybe there are better models, to find the model that works for me. Okay. In this case, I'm creating an iterative process that is trying to find the best models to create any signals of my data set. So let's say that you have lots of observation of your temperature. Okay, 1,000, not so lot, but 1 million observation of your temperature. Any observation can be represented, any observation, as a linear combination of some alpha that is similar to the A features that I defined before, and these that are the end members, that are the signal of my basis. Okay, and then there's some noise. So you have Y signals, but you don't know nothing about alpha and P. Okay, there's a way, iteratively, by some many iterations, that this is a blind and member abundance estimation problem, to solve it. So you start selecting an initial matrix of P, and then compute your abundances that are your alpha elements, your vector of alpha, and then you iteratively try to compute to find the best solution, the best end members, the best models that are able to characterize with n members any signal of your data set. So you are working with the data to estimate the model. Okay, you just need to say, I want n models for my problem. Let's say 3 models in 3 models. So 4 models if I have 4 classes, for example. Then the alpha are the features. Okay. So this is something that we already seen. Okay. So temperature decays and normalized contrast. And these are the end members estimated from the process, this extended blind member abundance estimation problem. Okay. These are the basis, and then any signal of temperature that you see on your surface will be represented as a linear combination of these 3 models. Okay, this is completely automatic. For example, so these are 3 end members. In case of 4 end members, so I can select any n, 4, 7, 10, 1 million, of course, a low number. So these are the abundance maps. So these have the same meaning of the feature maps that we have defined previously, A1, A2, and 3. Okay, so look at the data. The second abundance map is representing the first line. Sorry. The first abundance map maybe is representing the second line and something of the third, and the edges of the first line. This maybe is saying nothing, but here you see the background. So the fourth abundance map, so where is yellow is 1, blue is 0, okay, in this color scale. So yellow means that is the background. So the fourth abundance map maybe is the background. So this third, if we use all the abundance map for feeding a classifier, maybe we can also find, well, I have a good estimation of the third line, but if you see here, maybe also the fourth line with the same data that we used before for deep learning. Okay, so we are pushing, we are boosting the results, taking the experiments the same. Okay. For example, we just take this to all the shallow classifier and use a support vector machine that is very easy, something that was presented many, many years ago. So with a balanced classification accuracy that is now 92% on the same data set before that, there we reached 86.9, something like this. We are boosting the classification accuracy. And the recall is of 89%. Of course, there are many false positives because I decided to make to give some privilege to this metric for my reasons. Without any morphological filter, without any, let's say, trick about making, okay, let's make a 25% threshold to help the detection of class 3 defects. I'm not doing this. So these are direct results from this model. Okay. And there's another point that is very, very important. Once you have your model defined from the data and not from your knowledge or from the theory, you can also say, give a feedback for the experiment. I don't need all the time samples on the temperature decay, because maybe it's enough to stop my analysis, my experiments, instead of looking for 30 minutes, it's enough to stay there for 5 minutes. These groups of temperature are enough for my estimation. So we are changing the view and say, okay, I will take, for example, 150 samples. These are not seconds, so because we have made this normalization of the time axis, so maybe these are minutes. Not 150 minutes, of course, but 10 minutes, let's say. And say, okay, I can take just 10 minutes instead of 30 minutes for making my prediction and get some good result. And for example, with n equal to 200, sorry, we get, of course, test accuracy that is lower than before, but even acceptable. Or in this case, the test accuracy is almost the same. So we don't need to look at the whole temperature. So we're giving a feedback based on the interpretation of the end member. Interpretation of the end member is important. Sorry, interpretation is important. So when you work with deep learning, you have a kind of black box. Feed it, output, and then you say, okay, my accuracy. But you don't have the explainability where there are many, now there's a branch of research for explainable AI, okay. But in that case, it's very straightforward because you are saying, okay, here, these end members are almost the same. So there's no reason to look at all my signal, the whole signals. I can just take the first 50 samples and there stop my analysis. Okay, and this is very important because reducing instead of 30 minutes, 5 minutes in production line means money. Okay.
How can you choose the window?
For example, by making a parametric analysis and say, these are, for example, the test accuracy. And this is the recall of class 3. That is my target class. And say, okay, for example, 100 samples are enough to reach a kind of plateau of my metrics, of my accuracy, of my recall. Okay. Now, so this was published 6 months ago. So the point was, can we, instead of using a linear unmixing, okay, so create these models and then make this as a basis and make the abundances on this basis to create any signal of temperature of the world. Can I use the convolution? So the point is, let's say, in signal processing, anytime you have a material and you have some input, you can characterize the material with its impulse response. Okay, so that any output will be the impulse response convoluted by an input. Okay, I think that you should be aware of this. So the point is that instead of creating that representation with a basis for any kind of source contribution, can I understand which is, without knowing the source contribution, without knowing anything, without any a priori knowledge about the source contribution, can I estimate the impulse response of the material? So impulse response will depend on the defect and the geometry and the material. Point. Dot. That's it. Okay. The source will be whatever. Will be the flash lamp, would be the long pulse, could be the lock-in thermography, whatever. The only difference is, of course, that if you use a flash lamp, you can detect you can estimate the impulse response in the limit of your experiment, of course. So this is the idea, and these are the estimated impulse responses from different region, because there's a way, without knowing anything about the source, there's a way to estimate at the same time the source and the impulse response from the data, from your output. Okay.
You don't know the material.
You don't know nothing. You don't have any knowledge about this. These are temperature, but you don't, in theory, you don't know neither that this is a temperature. This works for everything. So, and again, it's an iterative process. There are many approximations, of course, but you can estimate at the same time. Knowing the output, you can estimate at the same time the input and your impulse response. Okay, so for example, these are impulse responses from sound, surface, mid-deep, and in-depth defects. Okay, and then these are, okay, once you get the estimated source and the estimated impulse response, you can also compute your estimated output based on these two outcomes that you get from your model, and then compare the estimated output with the actual one that was used to create the source and the impulse response. And this is the comparison. So blue circles that seem more a stripe than a circle are the estimated thermograms, the temperature signals, and in red the original measurement. Okay. Here for a surface defect. So here we are taking also into account, of course, the warm-up phase. So we are not just taking the cooling phase, but also the warm phase. So you are able to understand the source, that of course would be, the first approximation is that the source contribution is homogeneous on the whole points of your structure. But you can also estimate the impulse response. And now we are trying to create some classified, so this is a work of that I'm currently working on this. So we're trying to create some classification strategy to take the impulse response, and knowing the impulse response that I have these profiles, try to classify the depth of the defect. Okay. Now, what's the time? Can we have 5 minutes of break, or you want to take this last 30 minutes like this and then stop before? It's up to you. So just a few words about the examination. I actually don't know, but maybe. Preparing the exam. So the exam is something. Well, actually, I didn't know how to examine for this course. I cannot ask you for a project, or because maybe what I delivered to you was not enough to create to finish a project. Okay, in 20 hours, you know. But maybe you will be able to write a review paper. Well, there are 4, 6, 10 attendees, 10 students. Maybe you can also group in couples, even to make this exam easier. Okay, so what I want you to do is to write a review paper, not complete review paper. You can even copy from something in the literature. I will not make a plagiarism analysis of what you are doing of 4 pages in conference template. So this should be something that you will make with your left hand if you are right-handed. Okay. So these are some examples of the topics. for example, a comparison of the sensory equipment for thermography, a comparison of the experimental techniques. Let's say, I don't know, the question is, how can I make an excitation on my surface? It's better to use microwaves or lasers, and make a review paper about this. Okay, so try to use your fantasy to ask you a question and try to solve it in 4 pages in groups of 2. So maybe will not take so long to make this to earn this credit. Okay. Well, when are you going to earn your PhD title? I think for me, in let's say before summer. Okay, so in 2 months. I know that you have a lot of work to run experiments and so on. So I don't want to take your time, but let's say, okay. So if you need your credits tomorrow, please give me today in the evening your review paper, and I will say okay.
Also,
okay.
ChatGPT is bad here.
So depends. Now, 50 minutes to, I don't know, you have already written a paper. I'm not the best English speaker or writer in the world, but there are many rules that if nobody tell you about these rules, you can earn these rules with experience in the artificial intelligence approach, but maybe it's better to start with somebody that is giving you some suggestions. Okay.
Suggestion is called mentorship.
Okay, let's say like as you prefer.
Yes.
So you know that there are many kinds of papers. I want you to write, let's say, review, not review paper, review conference letter. Okay. So these are just some examples of papers. And since Siderius Nuncius by Galileo Galilei, and that's my present for you. So I printed some copy in Latin, Italian, and English. So select Italian, then Latin, and the English copies. Maybe another one. Because Galileo Galilei, that invented the scientific method, in 1610 wrote down maybe the first paper of the history, this Siderius Nuncius, in Latin. Why Latin? Because Latin was the official language, as we now write in English, because English is worldwide known. Of course, he is able to speak in Italian, but he preferred to write in Latin to reach more people. And if you see, I'm shy. If you see, so English, English, Italian, Latin. No, questo è okay.
I assume that the first publication was in Greek.
Yeah, there were a review paper by Polibio about optical communications, and this is very good. But you can find also this by Polibio.
But it's I remember Aristotle or Polybio, or I don't remember the name, but I think Greek.
But it was more, let's say, I don't want to say a review paper because there was an advancement with respect to the state of the art, also in this paper by Polibio. But this has figures. This has another structure, a more, let's say, modern structure.
Modern.
Okay. If you read this paper, you will find more or less the standard structure with an abstract that, let me, so in this, the abstract. In the short treatment, I propose great things for inspection and contemplation by every explorer of the nature. Great, I said, because of the excellence of things themselves, because of the new and so the abstract. If you see here that we discovered the satellites of Jove. Okay. And there's an abstract, then there's an introduction with the state of the art. I know that there was some Dutch that made some lenses to magnify the stars and so on. So there's an introduction with the state of the art, and then he presents the methodology. This is an experimental paper, let's say, with the equipment that he used, and then the results with the figures. He wrote actually the planets and the satellites and so on. So, starting from Galileo Galilei, we are using this structure for a paper. Now, the abstract, my suggestion is to make an abstract that is always self-explainable, even with the results, with the numbers. Because if I don't have time reading the abstract, I should know everything of your 20 pages paper. Okay, just looking at the abstract. So the abstract should take everything from the state of the art, where you are placing your work, what you are proposing, and the results that you get, and if possible, even the future works. Everything in your abstract should be self-explainable. So then, once I get, okay, this abstract works for me, I will read 20 pages of paper. Okay, then the introduction with the boundaries of your work, where you are placing your paper, where you are, where you want to go, what you are presenting. There's in some journals also require a related work section, where there's not the even papers. Can I say? So, for example, in computer science, when you propose something about a network, you typically must create a related work section in the introduction, where you present all the works that are similar to your work. Well, it could be a table, but also in 32, the authors present authors. They were but so, and try to highlight your, of course, your valuable contribution to the state of the art while you are presenting your work. Then the methodology, where you explain everything without giving numbers. So be general, okay. Or if you are making a paper on experiments, methodology is more the material and method section, okay, where you present the data set, for example, so starting from the equipment. So there are different ways of this methodology section. Results and discussions. So the body of the paper is methodology, result, and discussion. The rest is not noise, of course, but is something to place your work in the history, because we are standing on the shoulders of giants. We are not discovering, tomorrow we'll discover the hot water. No, we are working on advancements of somebody that has done a work before me. Results and discussion, where you should always comment on your findings, explain what data suggests, and highlight what is unexpected. These are the points. So maybe these comments are also the result of a round of revision with a referee. Why typically you submit your paper without, so even you maybe know that there is something strange in your results, and then a reviewer that is expert of your work will say, well, but in this figure, there's something that is unpredictable. Can you explain why you get these results? And then you are adding more in your discussion. Okay, so, but if you can also discuss everything before submitting your paper, before this round of review with your referees. Then the conclusions, acknowledgement, cite whoever has made a contribution to, well, we can open some parentheses also on the author list, but I don't want to go in the author list. It depends on you. Okay. Then the references, all the material, formatting, penalty journal, the appendix, when required, when it is required, for example, if there's a development of a theorem that you are using in your paper, you can add an appendix where you make the development of your theorem, let's say. Now, few words, because maybe you know what are research letters, conference proceeding, conference abstract, or book chapter.
So one thing, previous one, I submit a conference paper, so the reviewer had feedback, so they said the discussion is very less.
Maybe because you had 6 pages for your paper, and you don't know how.
No, the discussion only like one paragraph. Like
Okay.
All the thing is like statistical analysis. It's all about the methodology, how we apply the stats and what are the formulas and how the result outcome, how we discriminate the findings like that. So it doesn't have that much discussion left.
But discussion typically, so there's a problem that when you make a discussion, you typically refer to your results, numbers or plots, and say, okay, this works better than this. Discussion means that you should go in the meaning of your numbers. Try to understand if there's something, as I said before, unpredictable or something. Let's say, previously I said, okay, I'm presenting this fantastic work about the extended blind and member abundance and instruction, and say, okay, I'm having this impressive balanced accuracy. I can stop it. But the discussion is, I can use this knowledge for making a feedback for the experiments, for trying to give new information to who is setting up so that is not directly from the numbers. Numbers are good, okay, but then try to get an insight of your numbers and try to connect numbers to reality, to what is actually, for example, if you have that one methodology is working better than another, try to answer the question, why? And then write your discussion. Okay, so that's the point. So try to extrapolate more meanings from numbers.
It's difficult because
I know that is difficult, but you are studying for being a researcher. Okay, so a researcher maybe is somebody that is with his hand in the cloud and is trying to solve something, solve questions that nobody has asked, maybe, and try to give his answer with some exotic. Okay, so try to use your fantasy to see beyond the paper, beyond the results, beyond what you have. Okay, so go back here. So just, okay, the review paper. So I don't know if you are first year, second year, third year students. Maybe first year of your course is for a review paper. So you start with your activity, make a lot of analysis of the literature, and then say, okay, I've read 200 papers, I can write a review paper. Okay. Review paper is not only copying the abstract of any of these 200 papers and try to create a form that is consequence between sentences and publish it. It's more ask for a specific question and give your interpretation. Okay. Discuss for future directions. Try to. So you have read 200 papers. What have you catch from these papers? Which are the open challenges? Which is the problem that everybody should try to solve for making your research actually valuable and ready to market, let's say. Okay, so these are the questions that you should answer for a review paper, a good review paper. Okay, and if you look at two review papers, there's always a question behind the aim of the authors. Okay, then suggestions. Okay, not long sentences, but this is more related to English writing. An error is not to highlight the novelty of the paper. So when you have back a reviewer that is saying that your paper has no novelty, but you know that your paper is pushing the literature to the space, maybe you were not giving this novelty to. So it's better to say. So in the introduction, the last part of the introduction, or in the abstract, because the abstract should be self-everything. Say the novelty of the paper is this one, and make a bullet point if necessary. Okay, this should be, of course, this should be the truth, but it should be clearly visible by anybody that is going to read your paper. A title that is not focused, for example. So when you Google something about your research, you typically use few words. Try to put these few words in your paper title, okay? Because in that case, once anybody has the same problem of you, maybe is going to take your paper, and then you can increase your, of course, your citations. Or then add headings when unnecessary. I hate this. So if there's methodology 2.8 deep learning and then there's no 2.b, I don't know why you make 2.8. Okay. So headings, the separation of paragraphs in headings should be done when necessary. Okay. Methodology, if you are creating something with new deep learning, this methodology should be deep learning and not make a subsection without a division in another one. So make subsections when there are 3 subsections, not just one. Okay, there's no reason to make one subsection within. There's no reason. So what is done is in the past tense. Experiments were run when you discuss your experiments, for example. But what is done in the literature is in the present tense. Okay, in fact, the authors present a method because it's something that is assessed, is there in the literature, it will be there forever. Okay, present. Use not robust sources is from thesis of bachelor degree, not from papers of the PhD student. Do not cite something that you didn't read. Okay, so how many times you are writing down your introduction and you want to add 3 references about a point just to depict, for example, in thermography, there is a long pulse, and I want to add a reference about the long pulse thermography. And maybe start Google it and make, okay, the first one, I will take it as my reference without neither open the paper or read it. There was a time that it actually happened to a colleague of mine that received 2 years the publication of the paper. So the paper was published on 2020. In 2022, there was a communication of there are many websites that make this analysis of the citations. That one of the papers that were cited in this manuscript was let's say not probably a paper from some, was a kind of, how can I say,
Is it a report or industry report, or
I cannot remember which was the website that made this notification. But one of the paper was by an author that had with an H index of 15 with 15 papers. So that means that was something strange. And when we opened the paper, this was written in something that was not English. Okay, maybe written by my son. Okay, with words that were probably using a Google translator. I don't know. Mean square error was translated in mean square mistake. There were some sentences that, so opening this, even if this paper was published on a very important journal. So you say, okay, this paper has a good title, a good journal, I will cite it. Open the paper, because maybe there's a problem. So all this was from a special session from some editors that for their specific, how can I say, so they accepted lots of papers of low quality just to improve their metrics, their bibliographic metrics. Okay, so open the paper when you cite it. not just taking, because maybe you are, and then there's a problem because you need to make an addendum, and that's what we made. We made an addendum saying that we were not connected with that specific citation, that citation was not so important for a paper that was made there just for create a list of 40 references, okay? And that bad citation was not altering the quality of the rest of the paper, or the results were actually correct, even if I was citing this paper in the first sentence of introduction, okay? So, and it could happen. And don't use Google Translate blindly, or use totally ChatGPT that maybe now you are using for writing your.
It's bad.
Bad, but you can use a VPN and then go in the US and open your ChatGPT. Okay.
ChatGPT is very difficult. Earlier because it's all servers are full, so you have to wait.
Well, but if you ask for the good questions, you can have a very good introduction to your paper. But as I told you,
Previously, I tried it, but it's very good for ideas. You can have a lot of ideas, but you have to make a filter, like what idea is best for your.
Yeah, sure. And
But
then
it's good for collection of data. It's very good.
But for example, ChatGPT cannot give you the references.
Because it doesn't have access to the scientific papers, especially the costly papers, especially examples.
Well, but today many papers are open access, or
No, it can give references, but it's fake references.
okay, yeah, sure.
When you open it, it cannot open, it's fake.
But just another suggestion: once you have write down your paper, or well, better, before you write your paper, maybe you have just your abstract, your basic idea, and your title. Try to use these journal finders to find the best journal that matches your topics. Okay, there are some scores. You, for example, have a title and an abstract. You can go there in public. I don't know, publication recommended. I don't know if it opens. And put your keywords, your keyword for. There are many things that you can do, and there's a suggestion of the best journal for you. Okay, and maybe there in that journal you can also find other papers that maybe you were not using for your introduction or for your comparison and so on. For example, that one for the Elsevier, of course, it explores just the journals of the same editor. So you can write here your title, your abstract, and say find journals. And there's a match of you. Sorry?
It will not save data. It will not save data. Maybe if we.
Just for
instance, plagiarism, like if you save data in some servers or.
okay.
So if you publish, it may have plagiarized, like fake plagiarize or unintended plagiarism.
Yep.
It may happen
With this
with this methodology. Because
I agree.
someone told me that if you
Well, okay.
it may save, memorize the data.
It could be okay. Maybe if you accept everything, when there's the banner on the bottom of the page that makes you accept the cookies. And but I will not care about this. So if you are making your own research, for another one that interested in your research to get the same results of you, maybe it will take 1 year. So you have an advance in that research. So you are the owner, and that's it. Okay. Then Of course, once you have your we found your journal, maybe it's better to cite papers, for example, from this journal, to give more evidence to the fact that you are submitting to a journal that is centered on your topics. Okay. Then don't always aim high. That's a very good point. Maybe you're writing your paper and you say, but not the best in the world. Maybe it's better to go to some journal that with low impact factor or something like that. Try with the best journal of your subject category. Because maybe if you are good in writing and you are able to explain, to deliver the message in a good way with a very readable paper and something like this, you can also be accepted in papers with high impact factor, with the journal or by journals of high impact factor. Okay. Maybe, or on the contrary, you can also be rejected by journals of low impact factor because you were not so lucky to find a reviewer that was, let's say, a fair review. Okay. Because your reviewer is working on the same of you, and maybe is because it could happen, of course. And there are lists of predatory journals that are typically journals of low quality or a journal that gives you the acceptance notification in 2 weeks, or journals that need money for publications. So there are many points to define a journal as predatory. There are, so the best list is the worldwide known list of predatory journal. And of course, try to avoid the publication on this kind of journals, for sure. Then start with figures. So for me, it's easier to write a paper once the figures are established. Okay, this means that you have already done everything. So to get the figure 9 of your paper, you should have finished everything. Then another point, just be jealous of your first draft. So writing takes time. Okay, in 2 weeks, maybe you can write your paper and get, but take another week for read it again. So don't go to your supervisor and say, okay, I finish in 2 weeks, that's it, because maybe it's I'm recording. So maybe it's not the best paper in the world, because, okay, so read it again and again. So be jealous of your first draft. Nobody should see it. Okay. And then, for example, you can use some language assistant. There are many language assistants. If you use LaTeX or Overleaf, for example, that is online LaTeX, you can use Writeful. There are Grammarly, Jasper. There are many of these, or probably you already use it. So just to end this lecture, typically, write a paper could be the most boring part of your research. But this is part of the research. If we talk today about Galileo Galilei, is because Galileo Galilei wrote his Siderius Nuncius. If he didn't do that, we were completely, we didn't know nothing at all. So don't think that Leonardo da Vinci was the only one engineering in his epoch. There were many engineers in the epoch of Leonardo da Vinci, but we know about Leonardo da Vinci because we have his manuscripts. Okay, so if you want to to make your research, you then have to share this research with the others. And this is part of the research. Okay, I know that maybe it will be boring or maybe not. I love write paper, but it's part of your research. You are nobody if you don't write your paper. Okay, that's it. Now we have finished everything. I will ask you for this questionnaire of course evaluation, if you can fill it. I don't know if, so this should be anonymous, of course. I don't know if for those that are.
You can send the online, we can send it online also.
Yeah, I know, but I know your name. Maybe there's some.
Maybe a single person can collect.
But this one on the because we can.
But if you can fill this form now, it's,
Okay.
I print it for you.
Okay.
And then for this last lecture, you. So do you have any question about, not about this, of course, these are just, but about the research activities?
Don't want to take the exam because I have finished my courses with exam. I just want to get a
Attendance certificate, he needs attendance certificate only.
Okay, it's up to you. If you have the attendance of the lectures online or in person, you can get your credit.
But if you remember that, let's.
Yeah, no.
Some problems.
Yeah, no. Okay. I actually don't know how can I say that you were attending the course.
Let's say, for example, this student attended in the courses. And
Okay, but
you should send it as the email.
to who? To you?
Yes.
Okay, and that's it. And say, okay, send me a mail and say, okay, I need this certificate with a template, and I will give you back.
I really appreciate that. Also, I have attached template.
Okay. If you have it, let me. So we close it. And if there's any other question also from you at home, I will close everything. So bye. Ah, okay.